All right. Morning, everybody. Moving on to chapter 2, the first law of thermodynamics. First law of thermodynamics concerns these three things. Let's see if I can get my pencil to work. Work, heat, and energy. So what we're going to talk about is what these are and how we can change between these things. The big ideas here are conservation of energy. We'll learn how to assess the energy changes that accompany chemical and physical processes. And the really important topic is enthalpy. So we'll learn what enthalpy is, and again, how you can use this to record heat output of chemical and physical processes. All right, before we dig into things, if I can get my down arrows to work, we're going to define some terms. And this happens a lot in thermodynamics, things which seemingly have simple meanings, we actually need to define precisely, and the definitions are important. So we'll start with work. If I can switch my ink color, here we go. You may remember from your physics class that work is usually defined as motion against an opposing force. So here's a notebook. If I take my pen and I push my pen across it, there's some friction force between these things. I have to overcome that friction force and do some work. You may remember that the specific formula looks something like this. Work equals the integral of minus F dot dx, right? So it's force times distance, basically. That's work. Heat, if you were to Google heat, this is what you find. Quality of being hot, high temperature. It's actually not how we're going to define it in thermodynamics. It has a much more precise meaning. And the way that we're going to define it right now is it's a transfer of energy due to a temperature difference. If I have two objects, one hot and one cold, and I put them in contact with one another, heat will spontaneously transfer from the hot object to the cold object. So that is what heat is. Last but not least, we have energy. Again, your physics textbook will define energy as the ability to do work. That's a good definition. You should know it. It works, but it has no poetry to it. And so I wanted to tell you a brief story. This guy here, named Craig Topol, he was my lab partner in my freshman physics course. Craig was a really good guy, but he had zero interest in doing any physics. And so the deal that we sort of made was that I would do the physics, I like that, and Craig would get me into the good parties. And once early on in some physics lab, Craig was off in La La Land doing his thing. And this professor walked over and asked him what was going on, and then said to Craig, do you even know what energy is? And Craig stopped for a second, and he responded and said, energy is the thing that makes other things happen. And the professor kind of stopped and walked away, because it's a reasonable definition, right? I like that one. Craig is now a Presbyterian minister, and I think this is him after he got his theology degree. A little more scientific is this guy. This is Tesla. And Tesla said, if you want to find out the secret of the universe, think in terms of energy, frequency, and vibration. So energy is the secret of the universe. I like both of these a little bit more. All right, we need to define some other things. First up is system and surroundings. So here's my picture. The system is this, okay? It's the thing that we're interested in. It could be a piston with some gas in it. It could be a beaker with some chemical reaction going on inside of it. It could be a protein, right, inside of some cell. It's whatever unit we're interested in. The surroundings is everything else, right? So we can divide the whole universe up into system and surroundings. We can then subsequently classify systems and surroundings with some other useful definitions. Specifically, we'll talk about open, closed, and isolated systems. These pictures illustrate the meanings of these terms. An open system is one in which matter and energy can both cross between the two. A closed system is one in which energy can cross between the system and surroundings, but matter cannot. So the matter is all enclosed within the system. And last but not least, we have an isolated system in which neither matter nor energy can cross the boundary between the system and surroundings. Okay, we're now ready to start attacking some of these things, and we can define what we mean by energy a little bit more carefully. So specifically, we're going to define something called the internal energy U. And I'm not sure exactly how much writing I'm going to be doing, but in order to not confuse my U's with my V's, if you see me make a symbol like that, that's my U, right? The internal energy is the sum of the kinetic and potential energy of all constituents of the system. So if I have some collection of gas molecules and I add up all of the kinetic energy and all of the potential energy of every single molecule in the system, I get the internal energy. All right, let's start hashing this out. What is the potential energy of an ideal gas, and what is the kinetic energy of an ideal gas? Pause it for a second and think about this and check back in. Once you do that, what you might start to realize is that you can actually make some insights about these things. Remember that an ideal gas has no interactions. Molecules are bopping all around, but they don't interact. And so the potential energy of an ideal gas is zero, right? It has no intermolecular forces, no attractions or repulsions between molecules. Kinetic energy, well, you know this formula, 1/2 mv squared, right? And remember that velocity is actually measured by temperature. So when we think about the temperature of a gaseous system, right, what we're really thinking about is how fast the molecules are moving. And this leads to a really important insight. So if you're a kind of person who's taking notes, write this down. The internal energy of an ideal gas only depends on the temperature. Right? Temperature impacts velocity, velocity impacts kinetic energy, and that is the only game in town. Right? Therefore, the internal energy of an ideal gas only depends on temperature. Now, note that here we're talking about ideal gases. If we're talking about other systems like real gases, this idea doesn't stick, but ideal gases are a reasonable model for lots of things. And in fact, we can derive a formula for this. So I'm going to write this way. Kinetic energy is 1/2 mv squared. Right? Remember from our previous notes that v squared is 3/2 RT over m. Okay? This is defined per mole. This is per molecule. And so what you end up having to do is define this per mole, right? And you get something which looks like this, 1/2 N mv squared. Number of moles times the mass of one molecule is capital M. Crap. Get off there. And now rather than v squared, I'm going to plug this in here. 3/2 RT over M. Cancel, cancel. And what we get out at the end of the day is 3/2 nRT. The internal energy of a gas only depends on temperature. All right, a couple other notes here about internal energy. I just derived this formula for you. I want to make one note here that this actually only applies for monoatomic gases. I'll talk about this in some subsequent videos, but note that this formula is not universal. We can ask the question of what kind of variable is internal energy. Previously, we defined state variables, and temperature is a state variable. If you ask me what the temperature of a gas is, I can tell you, and I don't care what it was a minute ago. It's defined purely by the current state of the system. And because energy only depends on temperature, U is a state variable. You tell me the temperature, I can tell you the energy of the system. The other thing is that U is an extensive property. If I double the number of molecules of gas, you get twice as much energy in the system. So it's extensive. And you'll see this throughout the course. There's an intensive version of this called the molar internal energy, U sub m. It's also sometimes written like this, U bar. U sub m is U divided by N, number of moles, and that is simply 3/2 RT. So this is the internal energy per mole. With those definitions, we can move on to define the first law of thermodynamics. And I could talk about this at length because I think it's a fascinating historical subject. But basically, the first law of thermodynamics was formulated by this guy, James Joule. And what he was thinking about was how mechanical work related to heat. And so he developed these kind of systems where he had pulleys with weights on them. Let me switch my pointer. So here's a pulley with a weight, and it was connected to a paddle wheel, and he would do different amounts of work and watch how much the water would heat up. And what he ultimately realized was these two things, that heat and work were equivalent ways to change the energy of a system. And if he isolated the system, there was never any changes in the internal energy. He ultimately formulated these two observations into what we now know as the first law of thermodynamics. So the first law of thermodynamics says this: the internal energy of an isolated system is constant. The internal energy of an isolated system never changes, it's constant. More colloquially, what you might know is that the energy of the universe is constant. We say that the energy of the universe energy cannot be created or destroyed. The first law of thermodynamics is a statement of the conservation of energy. One of the things physical chemists want to do is put this stuff into mathematical terms. And in mathematical terms, it looks like this. Pointer options. And I am going to write this in big red letters because it's really important. Delta U equals Q plus energy. Delta U is the change in energy. Q is heat. W is work. So I can use these two ideas, heat and work, to change the energy of the system, but I can never destroy it. Right? And coming up, we'll talk about how we can do that and keep track of that stuff. All right, see you next time.